In this video I'm going to solve every question from the UKMT Intermediate Maths Challenge from 2021. That's one of the main maths challenges in the UK, usually taken by students aged 13 to 16, but often taken by younger students as well. And if you're preparing for that challenge, then take a look at my free course, Get Ready for the Intermediate Maths Challenge. In that course, you can practice all of these questions, as well as questions from other papers, and each question has a video hint and a full video solution, so you can have a go at the question, watch the hint if you're stuck, you can really get the best chance of answering it by yourself, you can then see if it's right and watch the video solutions. It's a really great way to prepare for the Intermediate Maths Challenge. And over at that courses website, I've got loads more courses to prepare for maths challenges and school maths as well, so I really hope that you'll take a look over there. But if you'd like to watch the solutions here on YouTube instead, I'll get on with them now. I'll put timestamps below so you can jump to the questions you need, or if you'd like to work through the whole paper with me here, then we'll start at question 1 and you can pause the video at the start of each solution. In question 1, you could just do the subtraction and the addition here, although you might want to change the order to add 2021 to 2425 first and then subtract 2223 to avoid thinking about negative numbers. But you can also just do this by thinking about the last digits of the numbers here. So if I add 2021 to 2425, it would end in a 1 plus 5, which is 6. And then if I subtract something that ends in a 3 from that, the last digit is going to be a 3. And the only one of the answers here that ends in a 3 is B, which is 2223. So, given this is a maths challenge question where we've got a multiple choice answers, I can say for sure that B is going to be the answer. Question 2, the day before yesterday was 2 days after the day before my birthday. Today is Thursday. On what day was my birthday? Bit of a confusing, slightly tongue-twisting question here. I think here I would just start writing out a little calendar. So if today is Thursday, then we're going to be looking at the day before yesterday, so that's going to be a Tuesday. The day before yesterday is going to be a Tuesday, so the day before yesterday is going to be a Monday. That's 2 days after, so it's 2 days after Saturday, and that's the day before my birthday. So Saturday is the day before my birthday, and so my birthday must be on a Sunday, and the answer is A. In question 3 here, we've just got to remember to work the brackets from the inside ones out. Right, so the innermost ones here are -2, and that would give me -4. And then if I look at these brackets, now I've got -2 minus -4, so that's -2 plus 4, which is just 2. And now I've got 2 minus, and then this bracket is -2 minus 2, so that one is -4. So I've got 2 minus -4, that's 2 plus 4, and then -2. So I'm left with 6 minus 2, which is 4, and that is the final answer. There are a couple of ways you could do this question. Basically, the question just says we've got a diagram as shown with the angles marked as shown, and we want to find VWX, which is this one in the middle. The key is, because we've got squares, we know that these are right angles. Here, 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 and here. Okay, there's more right angles, but these are the only ones we're going to need to use. So you've got a couple of options. You could, add extra lines in here and, again, make right angles here and here, and then you could use a quadrilateral to work out this one, and then use the circle to work out this one, and do the same on this side as well, and you could chase the angles around that way. I'm going to do it in perhaps an even more efficient way than that, which is actually to spot a very helpful polygon here, which is this one, U, P, Q, Y, X, W, V, U. Okay, and now if we count how many sides that's got, 1, 2, 3, 4, 5, 6, 7 sides. Okay, so we've got a heptagon. And we know that the sum of the interior angles of an n-sided shape is 180 times n minus 2, something we used in the junior maths challenge even. So here that's 180 times 5, which is 900. Okay, and now I actually know the other angles in here, because if this is 90 degrees, then that means this is 270, 360 minus 90, angles in a circle add up to 360, and this one is also 270. Okay, so if I add all these angles together, 270 plus 270 plus 62 plus 74 plus 90 plus 90 plus the one we're looking for, let's call it X, I should get 900. So I just need to add these together and subtract from 900. So I've got 540 here plus another 180 gives me 720, plus 74 is 794, and then plus 62 gives me 856. So I've got 856 plus x is 900, so x is 900 minus 856, which is 44, and the answer is A. April, May and June have 90 sweets between them. May has 3/4 of the number of sweets that June has. April has 2/3 of the number of sweets that May has. How many sweets does June have? Okay, so in the Intermediate Maths Challenge, we should jump to algebra a bit more quickly than in the Junior Maths Challenge. If you've done those, a lot of the questions, algebra just makes it a lot easier. So let's let x be the number of sweets that June has. May has 3/4 of the number that June has, so that would be 3/4 of x. And April has 2/3 of the number that May has, so that would be 2/3 of 3/4 of x, or 2/3 times 3/4 of x. Now 2/3 times 3/4, we can cancel the 3's and also cancel a 2 and see that that's just a half x. So we get the equation that when I add these together, the total number of sweets, x plus 3/4 x plus 1/2 x, that must equal 90 sweets in total. Now how you go about solving this equation, there's two possible routes. My favourite one, and one if you can get really good at can save you time, is actually to multiply this equation through by 4 before you start, rather than trying to combine the x's immediately. If I multiply everything by 4, I get 4x, and then 3/4 times 4 is 3, so that's 3x, and 1/2 times 4 is 2x. So I get 4x plus 3x plus 2x equals 90, and I've suddenly, oh sorry, I need to times the 90 by 4 as well to get 360, and suddenly I've got a nice equation. So I've got 9x is equal to 360, and then dividing by 9, I get x equals 40 degrees. Of course, I think a lot of people will do it this way, where we add the fractions together instead. So I've got 1 and 3/4 and a half, right, x, and if I add those together, a half is 2/4, so I've got 1 and 5/4, or 2 and 1/4, which I could write as 9 over 4. So I could also write 9 over 4x equals 90, and now I've just got to do x is equal to 90 divided by 9 over 4, dividing by a fraction, we turn it upside down and multiply, so 90 over 9 is 10, 10 times 4 is 40, and I get the same answer as before. But I do think this method really simplifies things and stops us having to worry too much about. In question 6, Kai has begun to list in ascending order the positive integers that are not factors of 240, and we want to know what's the 6th number on Kai's list. So if we start just listing the positive integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., I can cross out the ones that are factors. 1 is a factor of everything, it's obviously even, so 2 is a factor. We can see that 3 is a factor. Remember the digit sum test that says that if you add the digits together and it's a multiple of 3, then 3 is a factor. That test works for 9 as well. 2 plus 4 is 6. That's not a multiple of 9. So actually 9 will be on Kai's list. It's not a multiple of 9. Now, as I keep going through this list, I can just check them one by one. You might like to have the prime factorization of 240 handy, right? So I could write it as 24 times 10, or I could write it as 8 times 3 times 2 times 5. 8 is 2 cubed. Right, so I've got 2 cubed times 2 times 3 times 5, or 2 to the 4 times 3 times 5. Do it with a factor tree if you prefer, but the more you do this, the more you'll make arguments like this. And actually I can see now whether numbers are factors pretty quickly, because I've just got to see if I can get them out of the prime factorization. Right, so 4 is in there because 4 is 2 squared, and I've got a 2 to the 4, so I've definitely got a 2 squared in there. 5 is in there, so it's a multiple of 5. 6 is 2 times 3, well I've got a 2 and a 3, so 6 is a factor. 7 is not here, no 7s, so that's going to be in Kai's list. 8 is a factor, we can see that here. 10 is a factor because 2 times 5 is in there. 11, no 11s in the prime decomposition, so that's in Kai's list. 12 is 2 squared times 3, and I've got a 2 squared and a 3, so that's a factor. 13 is a prime that's not in the factorization, so that's in the list. 14 is 2 times 7. Well, there's no 7 in the prime factorization, so it can't be a multiple of 14. 15 is 3 times 5, so that's a factor. At this point, I can see the answer to the question is 17, because I've exhausted all of the options. but for completeness, let's say 16 is 2 to the power of 4, so it's a multiple of 16, and 17 is a prime that's not in the factorization. So that's the 1, 2, 3, 4, 5, 6th number in Kai's list, and the answer is E. No need to overcomplicate this one, we're just going to do the calculation. Improper fractions are the best for this sort of calculation. So 4 minus a quarter, that's 16 over 4, minus a quarter, that's 15 over 4, 2 minus a half, that's 4 over 2, minus 1 over 2, so that's 3 over 2. So I just need to do 15 over 4 divided by 3 over 2. That's the same as 15 over 4 times 2/3. And now if I cancel this down, 15 and 3 cancel to give 5, and the 2 and the 4 cancel to give 2, and 5 over 2 is 2.5, and so the answer is C. In this question I've just made the diagram a bit bigger, but we've got the diagram showing two 10 by 14 rectangles edge to edge, and they share a common vertex, so that's this one here. Also we've got the centre of this rectangle and the midpoint of this line, and we want to know what the distance here from O to M here is. Now to work out this distance, we're going to want to use Pythagoras' theorem on this triangle here. So if I can just work out the lengths of the other sides of the triangle, I can apply that. So they're 10 by 14 rectangles, so that's 10 by 14, and then this one must be 10 by 14 this way round. If M is the midpoint, that means that this is halfway along this line, so that's going to be a distance of 5 here. O is the centre of this rectangle, so it's also halfway along here, so this would be 7, giving a total length along here of 12. And then to get this distance from here to here, well, again, O is the centre of this rectangle, so this distance here is 5, this height is 14, so I must have a 9 as the length here. So I've got a right angle triangle with lengths 9, 12 and something, so we can apply Pythagoras' theorem to it. I'll give you an even quicker way in a second, but Pythagoras' theorem just says here that x squared is going to be 9 squared plus 12 squared, so that's 81 plus 144, which is 225. So x is the square root of 225, which perhaps you know is 15, or if not, you can try out some numbers of the right size, but knowing your square numbers up to 20 is very useful here. Perhaps an even easier way of doing this is if you're experienced with Pythagoras and you've thought about Pythagorean triples, you should know this triangle that's 3, 4, 5. Comes up all the time, right? 3 squared plus 4 squared is 5 squared. That's what we call a Pythagorean triple, where we've got an integer solution here to Pythagoras' theorem, or an example of Pythagoras' theorem where all the values are integers, right? And if you just scale that up by a scale factor of 3, right? 9 is 3 times 3, 12 is 4 times 3, so this triangle is just this one scaled up by 3, so this length is 5 times 3, which is 15. Again, if you want a really fast way of doing this that helps you get through to the later questions quickly, this is exactly the sort of thing you want to be spotting. Either way you do it, the answer here is B, 15. How many of the following statements are true? Okay, well, a prime multiplied by a prime number is always prime. We can show things are wrong very easily, right? So if I take a prime number like 5 and multiply it by another prime number, for example itself 5, I get 25. Actually, this is basically never true. You know, if I take a prime number and I multiply it by another prime number, I get something that's not prime. It's kind of what a prime means. To be prime, it's got its only factors, can be 1 in itself. So if you multiply two prime numbers together, you're going to get something that's not prime. So this one is definitely false. A square multiplied by a square is always a square. This is probably the hardest one to really convince yourself of out of these. You could try some examples like 4 times 9 is a square times a square, and you get another square. And if you keep trying it, it will always work because it's true. But if you really want to convince yourself it's true, you'd need to write something like, well, a square number in general is going to be x squared. If I multiply it by y squared, that will be the same thing as having x times y all squared here, right? For example, here you say 2 squared times 3 squared is 2 times 3 squared, which is 6 squared. So it is always the case that if you multiply a square by a square, you get a square. That one's true. An odd number multiplied by an odd number is always an odd number. Yeah, I think we know that's true from our basic experience. That you could prove it, but the maths challenge is not the place to be writing out proofs of things that we know to be true. We're under time constraints and we want to just get through this. So odd times odd is odd, even times even is even. They're both definitely true. So 3 out of 4 statements are true, and the answer is D3. The prime factor decomposition of 2021 is 43 times 47, and we're asked what's the value of 53 times 57. Now this isn't my favourite IMC question for a reason I'll tell you at the end, but the way that they're intending for us to do this question is to say something like, well, we know 43 times 47 is 2021, and if we jump to 53 times 47, well, that would be an extra 10 lots of 47 compared to 43 times 47. So that would be 2021 plus 10 lots of 47, which is 470. And then I could say 53 times 57, well, that'll be the same as before. What we've got extra now is 10 lots of 53. We've got 57 lots of 53 instead of 47 lots of 53. So I'm also going to add on 10 lots of 53, which is 530. Now 470 plus 530 is 1,000. So we just need to do 2021 plus 1,000, which gives us 3,021. And the answer is D. Now this isn't my favourite IMC question because for a maths challenge question here, you've got this information that you're given at the start, but we could just totally disregard it. And I think it might even be quicker to do the question if we just work out 53 times 57. If you can do a long multiplication pretty quickly here, 7 times 3 is 21, 7 times 5 is 35, plus 2 gives me 37. Put a 0 here, 5 times 3 is 15, 5 times 5 is 25, so add the 1 to give us 26. And then if I just add these together, I get 1, and then 12, and then 10, and then that gives me a 3, so I get 3,021. So actually just doing the multiplication is a very good option here. Question 11, we've got the line with equation y equals 2x plus 3. That's reflected in the x-axis, and we want to know what the new line's equation is. So we just do a rough sketch here. You don't have rulers and things in the maths challenge papers, but it only needs to be a very rough sketch of this line. If you know the form of the equation y equals mx plus c, you'll know that this is a line that has c is the y-intercept, so that would be 3, and it's going to have a gradient of 2. So every time it goes along 1, it's going to go up 2, and the line is going to look something a bit like that. So, you know, when I get to 1 here, it's going to be at 5, for example. You don't need to put this level of detail in. But if I reflect that in the x-axis, right, so this point is going to stay exactly where it is, and we're going to get a reflection something like this. So it's going to go through minus 3 here, and we can see you know, by the reflection here, 1, it will get down to minus 5, so the gradient is going to be minus 2. You might be able to see that without actually putting in a particular point. So using this same form, we've got a gradient of minus 2, and the y-intercept is minus 3, so we get y equals minus 2x minus 3, and so you do just need to know the form of the straight lines here, which is something we'll look at in the full course as well. Go for gold in the Intermediate Maths Challenge. Andrew calculates that 40% of 50% of x is equal to 20% of 30% of y, where x is not equal to 0, and then we want to know which of the following is true. Firstly, let's just notice that it says x is not equal to 0 here, because you could have, if x were 0 and y were also 0, then this would be satisfied and sort of all of these answers would be true. So we're looking for a non-trivial or non-zero solution here. So 40% of something is 0.4 times that thing, and 50% of something is 0.5 times that thing. So I've got 0.4 times 0.5 times x here. That's going to be equal to, well, 20% of 30% of y. That's 0.2 times 0.3 times y. There are different ways you could sort out the algebra at the end here. We've got some decimals that are a bit awkward. So one thing we could do is we could multiply the decimals together and then just do some division. You might just, even before you've written this down, like work out 40% to 50% by saying 10% to 50% is 5%, so 40% to 50% will be 20%. 0.4 times 0.5 is 0.2x, say. So you could get to like 0.2x here, and then 0.2 times 0.3 times y is 0.06y. And what I'd do at this step is either just do y as 0.2 divided by 0.06, but actually, so you could work that out, or just to get rid of the decimals, right? So if you've got awkward decimals, just multiply both sides by 100 here, right? If I do 0.2 times 100, I get 20x, and if I do 0.06 times 100, I get 6y. We could have just done that at the start, by the way. If you could times this by 100, it's like timesing 0.4 times 10 and 0.5 times 10. That would give you 4 times 5, which is 20. And the right-hand side by 100 is 0.2 times 10 times 0.3 times 10, which is 2 times 3, which is 6. Okay. There's loads of actual simplifications here, right, as well. If you notice this was 0.2x, you might just cancel the 0.2 with this side or something. Anyway, I've done it this way, and once we've got to 20x equals 6y, we look at the forms of the answers, and we see they're all y equal to something. So I just need to make y the subject here, so let's put the y on the left-hand side. 6y is equal to 20x. Divide both sides by 6, and we get y is equal to 20x over 6, and that simplifies down to 10x over 3, dividing top and bottom by 2, and then the answer there is E. What's the remainder when 1, 2, 3, 4, 5 times 5, 4, 3, 2, 1 is divided by 9? Now what we don't want to do here really is just to multiply these numbers together. That's going to be quite inefficient, although it would be one way of solving the problem. It might just cost you a bit of time. And divisibility tricks are things we should always be looking out for, and we cover those a lot more in the Go for Gold courses, both in the previous Junior Maths Challenge 1 and in the Intermediate Maths Challenge 1 that you can upgrade to from this course. And one of the divisibility tests is divisibility by 9, which maybe is what we would obviously think of going for here, and that says that if you sum the digits and you get a multiple of 9, then the number is a multiple of 9. But 1 plus 2 plus 3 plus 4 plus 5 is 15, it's not a multiple of 9. So neither of these are multiples of 9. But there's also the divisibility test for divisibility by 3, right? So the fact that when I do 1 plus 2 plus 3 plus 4 plus 5 and I get 15, the fact that this is a multiple of 3 means that this number 1, 2, 3, 4, 5 is a multiple of 3. 5, 4, 3, 2, 1 has the same digits, so 5, 4, 3, 2, 1. These are both multiples of 3. Okay, so when I multiply them together, 1, 2, 3, 4, 5 is going to be 3 times something, and 5, 4, 3, 2, 1 is going to be 3 times something. So if I do this times this, it's going to have a 3 times 3 in it, so it's going to be a multiple of 9. That means the remainder when you divide by 9 is going to be 0. The diagram shows a large square divided into squares of 3 different sizes, and we want to know what percentage of the large square is shaded. This is quite a tricky example of a question like this, because often in these questions we can just find a smallest square, divide everything into those small squares, and then sort of just count them up. That is possible here, but you have to go to really, really small squares to do that, and so fine if you've managed to do that, but probably that's not the way I'd go with this one. So I think I'd look at the outside here and say, well, I've got 5 squares, so let's just make the side length of this square 5. Actually, another good choice here would be just to make it a 10 by 10 square, because that's quite easy to write as a percentage. But we'll go 5 by 5. So each of these squares is just a 1 by 1 square. So I've got here 8 of them, so I've got 8 units that are shaded. And when I look at the sort of inside square here, this one is going to be 3 by 3, okay, because I've just taken off 1 unit here and here from the full 5. And if we think about how much of that inside square is shaded, well, let's say I took these 2 shaded parts and put them in here, then you could see that exactly 3/4 of that inside square would be shaded in total. So the number of squares we've got is 8 plus 3/4 times the 3 by 3 square, which is 9. So we've got 8 plus 27 over 4. So if I write 8 as 32 over 4, you can see that the number of squares shaded is going to be 59 over 4. Now, this was a 5 by 5 square, so I want to sort of now say divide this by 25, if you like. But what I could do instead then, well, I suppose dividing by 25 is the same as multiplying it by 1 over 25. So perhaps it's not too hard to write it down like this actually, and then multiplying these together, I get 59 over 100, and so we can see that the percentage here is 59%. Of course, if we'd started by making this a 10 by 10 square, we'd have just got that the area is 59 straight away. So that would also have been a good option. we would have had 8 2 by, these would now be 4 units squared, that would have been 2 by 2 squares, so we'd have got 32, and the middle part here would have been 3/4 of a 6 by 6, which is 3/4 of 36, which gives us 32 plus 27, which is 59. So maybe actually making it a 10 by 10 square was useful there. But either way, we can get to the answer, and it's B, 59%. I've got a tricky question here. It says Patrick drives from P to Q at an average speed of 40 miles an hour, and his drive back from Q to P is an average speed of 45 miles per hour and takes 2 minutes less. Now, a couple of things to notice here. The speeds are in miles per hour, and the time is in minutes here, so we definitely want to convert either the speeds to miles per minute or 2 minutes into hours. So you could say 2 minutes is 1/30 of an hour. I think actually what I'm going to do here is say instead that 40 miles per hour is 40 over 60, which is 2/3. Okay, right, 40 over 60 miles per minute, if you like, and so that's 2/3. Let's write MPM, not really standard, but let's write MPM for miles per minute, and 45 miles per hour. That means you're going to go 45 over 60, or 3/4 of a mile per minute. And now I can just say everything's in miles and minutes here. So we've got speed equals distance over time. And as we're going to be thinking about the time here, let's rearrange this to give time equals distance over speed. And you can use the, some people like to write this as like a triangle. Speed equals distance over time, like this or something. So I'm crossing out the time here and saying, oh, that's distance over speed. Anyway, however you remember that is fine. And so on the way out, the time t is going to be the distance, which we'll just call x, which is the same on the way out as it is on the way back, of course, divided by the speed, which we have got as 2/3. Okay, so dividing by a fraction, you turn the fraction upside down and multiply. So this is 3 over 2x. And on the way back, the time is going to be t minus 2. That's x divided by 3/4, distance over time, which is 4/3 x. Okay, so on the one hand, I've got 3 over 2x is equal to the time. And if I rearrange this one, I've got 4 over 3x plus 2 is the time. So these are both expressions for the time. So they t that he takes to go on the first leg of the journey. So if I just set these equal to each other, let's write that up here. I've got 3 over 2x is equal to 4/3 x plus 2. So I just need to say, to get x, well, I've got 3 over 2x minus 4/3 x is equal to 2. If we put these both as sixths, then that's 9/6 x minus 8/6 x is equal to 2. So if I just multiply both sides of this equation by 6, I just get 9x minus 8x equals 2, so 12, and 9x minus 8x is equal to x, so the distance x is equal to 12. You might be able to do this algebra slightly more quickly and efficiently than I've done it there, and different ways of rearranging things here, but the idea here is that you want to write down two equations, whether you do it in hours or minutes or whatever, make sure it's consistent, eliminate t, and then you'll find the answer. And the answer here then is D, 12. Question 16, we've got a semicircle drawn on each side of a square as shown. The square has side length 2 pi, and we want to know what the area of the resulting shape is here. I've just made a slightly bigger copy of the diagram to look at. Right, the area of the square is pretty straightforward, right? I just do 2 pi times 2 pi, and that's 4 pi squared. And for a circle, we know the formula that the area is equal to pi r squared. So each of these semicircles is equal, so if I've got 4 of them, in total I've got 2 circles. So do I know the radius of those circles? Well, yes, because the radius of one of these circles is just half the side length of the square, so it's just pi. So actually these circles here are pi times pi squared, which is pi cubed. So the total area here is the square, which is 4 pi squared, and 2 full circles, or 4 semicircles. So that gives me 2 pi cubed. Now, to get the final answer here, we can see they've just factorized them. So factorizing here is just the same as with pi here as if it was with x to get the final answer, so I can see a common factor of a pi squared, and there's a common factor of a 2. 2 pi squared times 2 would be 4 pi squared, and 2 pi squared times pi would give us 2 pi cubed, so that's 2 pi squared times 2 plus pi, and that's the same thing here as 2 pi squared times pi plus 2, which is the answer here, E. In question 17, we've got a rectangle PQRS, and we're told things about the side lengths, so I should certainly try to draw a diagram of this. Now it says PQ is the shorter side, so let's label it like this, PQRS. We always label the sides in order like that. So this side is length 2, this side is length 4, and we've got points T and U inside the rectangle, so that PQT and RSU are equilateral triangles. So we're going to have them coming in something like this. I'm just going to do this approximately, and these aren't going to meet, okay, because this side length is 4, and all of these side lengths are going to be 2. Again, I'm not trying to draw this to scale at all, but certainly they're not going to be long enough to meet here. So what can we do? We want to work out the area of quadrilateral QRUT. Okay, so they're the points T and U. So I want the area of this quadrilateral here. 2 approaches we can take. We can either say, well, it's a trapezium, right, QRUT, so we can use the formula for the area of a trapezium, half A plus B times H here, where this would be, A, this would be B, and the height would be just the height that takes us up to here. And that height, of course, is going to be 1 because it's a half of 2. But we'd need to work out A, which we can do. Alternatively, we could say we've got two identical trapeziums and 2 identical triangles. So if I took the area of the rectangle and I subtract the area of the triangles, I'll end up with 2 trapeziums. So I could just half that to get the area of 1 trapezium. So we'll do that both ways. The maths turns out to be very similar. The real thing we need to do, though, is to work out this length, either this length A or the area of the triangle. And we can do that by splitting the triangle here in 2. In the full course, we do a lot more work on getting these lengths from particular types of triangles and talk about what we need in terms of the trigonometry for the Intermediate Maths Challenge. For here, so do take a look at the full course Go for Gold and the Intermediate Maths Challenge if you haven't already. And here we've got a right angle triangle. We've got the hypotenuse is 1, and this side length is sorry, the hypotenuse is 2, and this side length is 1. So we can just apply Pythagoras' theorem here to say that 1 squared plus x squared is 2 squared. So x squared is 4 minus 1, which is 3. So that side length would be the square root of 3. And we've got an identical situation on the other side here. So if the whole length of this rectangle is 4, then that side A would be 4 minus 2 lots of root 3. And then we can just use this formula for the area of the trapezium to say the area will be a half times 4 minus 2 root 3. And then I can add on the B, which is 4, multiply by H, which is times by 1, so I don't need to write anything here. So I've got a half of 8 minus 2 root 3. And so the answer here is just 4 minus root 3, which is D. As I said, you could also just say, oh, if you look at this equilateral triangle, once you've got the height here is root 3, and we can take this one as the base of 2, then the area is just a half base times height, half times 2 times root 3, which is root 3. So like the area of these two trapezia combined would be the area of the rectangle, which would be 8. Let me just clear a little bit of space here. Which would be 8 minus those 2 triangles, which is 2 root 3. That would leave us with those 2. And so to get just one of the trapezium, because they're identical, I can just take a half of it, and I've got exactly the same calculation as we had here, and we end up with 4 minus root 3 in exactly the same way. So either way, it's fine then. Question 18, which of these is closest in size to 1? So let's just write these out a little bit more, make sure we understand what these recurring decimals mean. So this one will be 0.959595, etc. This one's going to be 1.050505, etc. This one's going to be 0.960960. This one's going to be 1.040040. this final one is going to be 0.955555, like that. So we want to know which of these is closest to 1. So let's look at the ones that are bigger than 1 first. Well, we can clearly see out of B and D that B is further from 1 than D is, because it's bigger than 1 and it's larger, so we're not going to say the answer is B. Out of the ones that are smaller than 1, now the closest one, well, this one's 0.95, this one's 0.96, this one's 0.5 again, so actually the closest one to 1 from underneath is clearly this one here, 0.960960. So the race now is just between C and D. Which one of these is closer? Well, D is 1 plus 0.04 plus, whatever else that I get here, whereas C is 1 minus 0.04 and then plus 0.0960. So in C, I go 0.04 away from 1, and then adding something back on pulls me a bit closer to 1, whereas in D, I'm adding on 0.04, and then I'm adding on something that takes me further away from 1. So C is closer than 0.04 to 1, whereas D is further away than 0.04 to 1. So we can rule out D, and then the answer here is C. The diagram shows two overlapping rectangles, each measuring p by q. The area of the overlap is exactly 1/4 of the total area of the figure, and then we want to know what's the ratio of p to q. So don't get too far ahead of yourself in this question, just do it one step at a time. Let's just write down all of the relevant areas. So firstly, this square in the middle is clearly area q squared, right? This length is q, and it's an overlapping square here, because if that's q, that's also q, they're identical rectangles. Each of the individual rectangles has area p times q, right? So if I took the total area by doing like this rectangle plus this rectangle, I would overcount by this square here, right? So I'd have counted that bit twice. So the total area of the figure is 2pq minus q squared. So the area of the overlap, which is q squared, is equal to exactly 1/4 of this total area, and that gives me this equation that relates q and p. If I multiply both sides by 4, I get 4q squared is equal to 2pq minus q squared. So I can add q squared to both sides to get 5q squared is equal to 2p times q. And if we divide by q, assuming as we must that q is not 0, then 5q is going to be equal to 2p. You can kind of see the 5 and the 2 in the answer here now, and looking at the answers, you can probably convince yourself that the ratio is 5 to 2, and that's exactly right. If 5 times q is 2 times p, that's exactly what it means for it to be in the ratio, for p and q here to be in the ratio 5 to 2. If you're not convinced with converting it to the ratio, some people might like to write something like q is equal to 2/5 p, and then you could see if I did the ratio of p to q, if p is 1, then q is 2/5 of that, and then multiplying both sides by 5, you get 5 to 2. No need to do that, I just know that some people like to think about it like that. Once you see the 5 and the 2 here, we can say that the answer is A. Two straight lines have equations y equals px plus 4 and py equals qx minus 7, where p and q are constants, and we're told the lines meet at the point 3, 1, and we want to work out the value of q. If you don't overthink this question, and you get the first step right, it's actually quite easy, but it's easy to get bogged down by trying to think about what these lines actually look like and trying to draw them or something. The only idea we want to use here is that if the line passes through a point that's got these coordinates 3, 1, then when I plug the x and the y coordinates as x equals 3 and y equals 1 into their equations, that must work. So the fact that 3, 1 is on this first line, y is equal to px plus 4, well, if I put in x equals 3, that will give me 3p plus 4, and then y equals 1 here. I'll get an equation that will just tell me what p is straight away. 1 equals 3p plus 4. So that's minus 3 equals 3p, and so p is equal to minus 1. Now if I do the same with the other equation, py equals qx minus 7, well, y is 1 here, so p times 1 is p. I've got q times x, q times 3, so that's 3q minus 7. We already know that p is minus 1 now, so I've got minus 1 equals 3q minus 7. Add 7 to each side, I get 6 equals 3q, and divide by 3, and I get q is equal to 2. So actually, if you make sure you keep this a totally algebraic question, just using that idea that the graph of an equation is just the set of all of the points that satisfy the equation, whose coordinates satisfy the equation, substitute the coordinates into the equations, they're on both lines, so that gives us P and Q directly here. So we've got Q equals 2, and the answer is B. The key result we want to use here is one about area scale factors. That says if you've got similar shapes, that the areas scale up in proportion to the square of the way that the lengths scale up. I'll show you in the context of this question what I mean by that now. So we've got these 4 types of triangle, right? We've got the one that's got area 1, we've got one that's got area 9, we've got one that's got area 16, and then if we could work out the area of the big triangle, we could work out the area of this inner hexagon. So we can see that the area here, from the first one to the second one, scales up by a factor of 9. Right? 9 is 3 squared. So whatever the length of the side of the original triangle is here, let's call it x, then this one must have length 3x. Similarly, if I go from the first one to the last one here, there's a scale factor of 16, and 16 is 4 squared, so the length of this triangle must be 4 times the length of the original one. And what we can see on the picture is that the large triangle is made, the one side of it is made up of a side of the smallest one, the middle one, and the third one here. So actually the total length of this one must be 1x plus 3x plus 4x, which is 8x, and that means that the scale factor from here to here is going to be 8 squared, because the length scale factor is 8, so I mean the area scale factor from here to here is 8 squared, which is 64, and so the area of this large triangle must be 64. Now then, just to get the answer to the question, the inner hexagon is just that large triangle 64. If we just focus on this one, say minus each of those smaller ones, so we're going to subtract 1, 9 and 16, so that's 64 minus 26 in total, so that gets us to 38, and so the answer must be D. If you start trying to multiply out this expression as it is, you're going to end up with something very complicated. So what I want to do here is to look at each individual bracket and see if we can write it in a simpler way. So 1 plus 1 over x, right, I could say the 1 is x over x, so I've got x over x plus 1 over x, and that gives me x plus 1 over x. For 1 minus 2 over x plus 1, if we try and do the same thing, okay, if I put it over the denominator x plus 1, I'd have x plus 1 over x plus 1 minus 2 over x plus 1, and that's going to give x plus 1 minus 2 on the top, so that's x minus 1 over x plus 1. And then for the final one, 1 plus 2 over x minus 1, that's going to be x minus 1 over x minus 1 plus 2 over x minus 1, so that will give me x plus 1 over x minus 1. So when I multiply all these together, the product is going to be x plus 1 over x multiplied by x minus 1 over x plus 1 multiplied by x plus 1 over x minus 1. I don't really like using the times sign here, actually it's a bit unnecessary and looks a bit like an x, so let's just get rid of that, or maybe we can use a dot for times if you want to. Now you can see things cancel here, so I've got an x plus 1 cancelling with an x plus 1, got an x minus 1 cancelling with an x minus 1, and I'm left here just with x plus 1 over x, and no more rearrangement is needed because that's one of the answers here, and the answer is E. So we've got a semicircle and another kind of semicircular arc here. So the first semicircle has radius 2, and so the first thing I'd want to do here is to put in this line so we can work out the radius of the semicircle that has the shaded part in it. So this is a radius here, this is also a radius, so that would be 2, and then you've got Pythagoras theorem on this right angled triangle here, which says that, you know, the this x here would satisfy x squared equals 2 squared plus 2 squared, so x squared is equal to 8, or x is equal to the square root of 8. Really handy to be able to just do a little bit of simplification of surds for the IMC, as we'll talk about in the Go for Gold in the IMC course, and that here is the thing we want to do is to write root 8 as root 4 times root 2, so we can just say, oh, that's 2 root 2, okay? Because what that means is I can say this diameter is 2 root 2, and then the radius is half of it, so the radius of this circle that this semicircular arc comes from is root 2. Okay, so that means that the area of the whole semicircle, like this whole bit including these two parts here, would just be a half of that circle. The area of a circle is pi r squared, so here that would be pi times root 2 squared, which is just 2 pi, and I want a half of that for the semicircle, so 2 pi over 2 gives me pi for the area of, let me just write this, let's write that as a, b and c, right, so the area, so the a plus b would give me pi. So actually what I want to do is to work out the area of b, so I can sort of subtract that off. So to get the area of b, I would just look at the original circle and say, okay, the quarter of the circle, you know, b plus c here is pi r squared over 4. It's a quarter of that circle where r this time is 2. Okay, so I've got pi times 4, or 4 pi over 4, which is pi. Okay, but the area of C is just a triangle, half base times height, so half times 2 is equal to 2. So actually, the area of B here is pi minus 2, the quarter of the circle minus the triangle, and that means finally that the area of A is, pi minus the area of B, which is pi minus 2, so the pi's cancel out here, and we get a nice exact answer of 2. So the answer here is B, 2. Sam writes on a whiteboard all the positive integers from 1 to 6 inclusive once, and then also P5s and Q7s, and then the mean is 5.3. So I'm just going to write that down algebraically, right? The mean is always the total divided by n, where n is like the number of numbers, right? So if I add these numbers together, we're going to do 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then we're going to have P5s, so they'll add together to give 5 times P, and Q7s, so that'll add together to give 7 times Q, and the total is going to be, well, there's 6 plus P plus Q numbers here, so that will be the total, and we need that total to be equal to 5.3. So if you add these numbers together, you get 21, so we've got 21 plus 5P plus 7Q divided by 6 plus P plus Q is equal to 5.3. So if we multiply both sides by 6 plus P plus Q, that will clear out the denominator here. So we can just get rid of that. Oh, I rubbed out the P by mistake. So we've got something like this. I would probably prefer just to multiply this all by 10, so I don't have any fractions here. So 21 plus 50p plus 70q is equal to 53 times all of this. So we multiply that out. 53 times 6 gives us 318. And then I've got 53p and 53q. So if we tidy this up a little bit, subtract 50p from each side, I'm going to have 3p here. Subtract 53q from each side, I'm going to have 17q here. And 318 minus 210 is 108. Now we're always looking out for common factors and things in maths challenge questions. In this sort of question, for sure, what I notice here is the right-hand side has a factor of 3. Quickly looking at the divisibility test for 108, 1 plus 8 is 9. 9 is a multiple of 3, so I know this is a multiple of 3. So I get 3 here times p plus 36. So the thing I notice here now is that for this to work, q is going to have to be a multiple of 3, right? P and q have to be integers here. Because the right-hand side is a multiple of 3, so q needs to be a multiple of 3. Now, if I took q equals 3, well, actually, you could just ignore that because there's no option for that in the question. But if you took q equals 3, actually this number wouldn't be big enough. P would have to be negative then, because 17 times 3 is only 51, so to make this work it would have to be negative. So the first one that works is q is equal to 9. If I do 17 times 9 for 17q, that gives me 153. And actually then I could make 3, so then 3p would be 153 minus 108, which is 45, so that would work with p equals 15. So we can make this work with q equals 9, and the answer is B. So in this question, we're really just going to use this formula speed equals distance over time over and over again, but it is a tricky question, so we will have to take quite a lot of care. So Thomas has these constant speeds for both running and walking. So let's call his running speed V and his walking speed W. And it says when the down escalator is moving, so the escalator is going to be also having a certain speed that it's moving at. Let's call that E for escalator. then he can run down it in 15 seconds or walk down it in 30 seconds. So let's write speed equals distance over time for each of these pieces of information. So if he's running down the escalator, he's going to be getting his running speed and also the speed of the escalator. They will combine together to give his total speed. Okay, so we'll have that v plus e is equal to, now we don't know the length of the escalator, so let's just call that x and say that and divide that by 15. If you want to here, you could just give x a number. You could say x is 1 or 100 or whatever makes it convenient, because if you think about it, the length of the escalator actually can't really matter for this question. Anyway, we'll leave it as x just to be reassuring here in case we're not confident that we could take any value of it, because that requires quite a lot of intuition, I think, and we'll be able to do it quite neatly anyway. Right, so that's v plus e is x over 15, and he can also walk down it in 30 seconds, so his speed walking down it would be w plus e, right, so that'll be x over 30, and it says when the escalator was broken, it took him 20 seconds to run down it. Okay, so that means he's just running down it, so his speed will be v, so we know that v is equal to x over 20. Right, there's various ways you can do the algebra here, but what I really want to do here is to work out his walking speed down the escalator. So if I could actually form something, a very similar equation like this, right, I could just do w equals x over some number here, then I'd have exactly the same sort of equation, and this would be the time it takes him to go down the escalator. So I'm going to do this in a very neat way. We could just write that w here is, well, I know w plus e, right, and I could subtract v plus e from it, right, and then the e's would cancel out, right. If I just multiply out these brackets, that would give me w minus v, and then I've got e minus e, so this would be just w minus v, right. So if I just add v to that as well, then I'm just left with w. Okay, but all of these things I know. Okay, so w plus e is x over 30, v plus e is x over 15, and v is x over 20. So again, as I said, the x really doesn't matter here at all. I'm just going to factorize it out of this expression, in fact. So it's x times 1/30th minus 1/15th plus 1/20th. If I put all those over a common denominator, I'm going to get 2/60ths minus 4/60ths plus 3/60ths. 60 is the lowest common multiple of 15, 20, and 30. So that gives me x times 5 minus 4, or 1/60th. Okay, so I've got that the walking speed is equal to x over 60. So again, whatever the distance of the escalator here is, the time taken is going to be 60 seconds, and so the answer is E, 60. So very hard question. Lots of ways you could do the algebra at the end there, by the way. So however you've done it, if you've got the answer, really well done.